Welcome back to a review of my channel, _exe. Today we're going to look at more number patterns and sequences problems. Although this first question may not be necessarily related to number patterns and sequences, but it is related to patterns in general. So let's just jump into it. For question 1, John wrote two operations in his coding website. He called them the operations read and write. So here are the following inputs and outputs that each operation does. So we have a certain arbitrary integer x, and then we have its output read of x. So that's how you read that. So for example, 17 will give us an output of this number. Now the pattern here has to do with these letters. These letters that read the original number input. So for example, 61, it will read as so. And this has something to do with the outputs that it is given there. So I let you guys just experiment on the first part, which is the read operation. For the second part is the write operation. So we're given a certain input. For example, this number will give us 17. And 226 will give us 11. And this number will give us 27. Alright, so based on the given pattern above and given the operations above, find the value of each operation below. So if you found the pattern behind each of these operations, go ahead and evaluate each of the following. So I have read of 40, write of 2021. We have this composite operation, write of this number, and then finally read of write of 6. And then for part B, we need to find the product of the minimum and maximum values of n such that the digits of n are non-zero and the write evaluated at n is equal to 8. So all of these questions are strongly related to the pattern behind each operations here. So I'll just reveal the pattern here. So first observation for the read operation is that the inputs of these numbers correspond to the very first digits of this output number. And that looks pretty good. Secondly, as I've said, the letters that reads the original number input, for example 17, actually there are 9 letters in the word 17. It actually corresponds to this number here. So it's the digit or number after the first couple of digits of the original number input. So another example is 61. Notice that this has 8 letters and it corresponds to this number. 9 on the other hand has 4 letters and is corresponding to this. But what about the last couple of digits here? Well, if you notice, these last couple of digits actually corresponds to the product of the input number, which is the very first couple of digits, and the number of letters that the number has, which will be these numbers. So notice that 17 times 9 is equal to 153, 61 times 8 is equal to 488, 9 times 4 is equal to 36. So I hope that makes things clear. And let's jump into the write operation, which is fortunately 100 times easier. So notice here, if you take the sum of the digits of the input x, so in this case it will be 1 plus 3 plus 8 plus 1 plus 0 plus 4, which will be 17. This is exactly our output, sorry. So another example is 236. The sum of digits is 11, is exactly that. And 459,405, has the sum of its digits being equal to 27, and that is exactly that. So now we have determined the patterns of each operation. Let's evaluate the following. So let's just start with part 1 of part A, which is read of 40. Now you may need to write how 40 reads in the alphabet, which will be as so. So F-O-R-T-Y, 40. And notice these has 5 letters. So like on the pattern on the above, it will be the first couple of digits of the original input, and then after that followed by the number of letters, and then after that the product of these two numbers there, which will be 200. Alright, so that's that. And for second part, which is write of 2021, which will be the sum of digits of 2021, which will equal to 5. That's pretty easy. And for part 3, this is where things get a little bit interesting, because this is actually a composite function. So if write of this number, so there are 2009s. Now when you're dealing with composite functions, you must deal with the inside part first. So I'll just rewrite the outer part, which is right of the result of the inner part, which will be the sum of the digits of this number, and that is not as easy, and this is not hard to see. That is equal to 9 plus 9 plus all the way up to 9 2000 times. Or you can just change that as a product. So that would be right of 18,000, which evaluated that on the right operation will give us 9, since the sum of the digits of this number is 9. Alright, so that's it for part 3. Now for part 4, which is yet another composite function, in this case read of write of read of 6. So I'll just rewrite the question for you guys. Alright, so as in the strategy above, we need to deal with this inner part first. So that would be read of write of read 6, which will be, like on the pattern above, we can write 6 in its alphabet form, which is 6. There are 3 letters in the word 6, so our read of 6 value will be 6. That's the digit of the input, and then after that followed by 3, and then after that the product of these two numbers, which will be 18. And write of write of this number will be the sum of the digits of that number. So that will be read of, that will be 18. Now read of 18, we need to write 18 in the alphabet form. So it'll be 18. So there will be 8 letters, and that will be 18, 8. 18 times 8 will be 144. There we go. So this is our value. And for part B, we need to find the product of the minimum and maximum values of n such that the digits of n are non-zero, and the right function evaluated at n is equal to 8. So I think this is a bit of a miswriting, so that should be an 8. Alright, so let's just uh, explore for the maximum values. So the maximum values of n occurs when the number of digits of n is maximum as well. And you can see that the maximum digits of n must be equal to 8. So that number with 8 digits that satisfies the right of n is equal to 8, it will be this number there. So it will be 11,111,111. And you can check that no other possible solutions n is bigger than that. But you may be asking, well, you can just add a 0 there. That will make right of n is still equal to 8. And in fact, you can add another 0 that will still remain the same. You can add infinitely many zeros and therefore making it to be a maximum. However, if you reread the criteria of the question, the digits of n are non-zero. So therefore, you cannot add zeros, unfortunately. On the other hand, the minimum value of n occurs when the number of digits of n is minimized. And we can set the number of digits of n to be 1, and therefore the value of n that satisfies this must be equal to 8. And the product of these two will be 88,888,888. And that is our answer for part B. And that concludes question 1. And that's a pretty long one. And let's just jump into the second question. Right, for question 2, consider a sequence A1, A2, A3, and 4, and so on with the definition such that A of n, and I should have said this, but n must be a positive integer, so A of n is either 2n minus 1 or 4n plus 1. And you may notice that this looks like a piecewise definition for a sequence, and it's very similar to a piecewise definition for a function. So basically what a piecewise definition is a group of definitions according to different domains. So as you can see, the domain for the first definition, 2n minus 1, is n is less than or equal to 198, and the second definition applies when n is greater than 198. So that's just a brief explanation for this type of sequence. And we need to find the sum of the first 300 terms of A of n. So it will be A of 1 plus all the way up to A of 300. Now that expression, so we can just write A of 1 plus all the way up to A of 300. Well, that would probably be tiring, as you must have to calculate each value of A. However, we can fix this by rewriting this as a summation, or in the form of a sigma. So we can suppose a variable k equals to 1 to 300. So this basically means the sum of a certain function evaluated from k equals 1 to k equals 300. So it's basically the sum of that. So we can have A of k there. So notice if you deform this, you will have a result exactly like so. And I'm just going to rewrite this sigma or summation slightly differently. We can rewrite this as two different summations, but with different bounds. So you can rewrite that as follows. So again, if you combine these two summations together, you end up with the first one. And the reason we're doing this because we want to separate each of these functions into its corresponding domain. So the first summation is especially for this first domain, while the second function or summation will correspond to this domain there. So it's just like correcting the domains or making the summations to be equal to the domains, or yeah, something like that. And we can just substitute the value of a of k based on its corresponding definition of each domain. So for the first one, it is 2n minus 1 or 2k minus 1 in this case, since it satisfies this domain here. And on the other hand, the second summation, so of k, I'll just put a parenthesis there, just not to confuse you guys. So k goes from 199 to 300. That will be 4k plus 1. There we go. Alright, so there are many ways to evaluate each of these summations, and here is one of them. So I'm just going to use some summation properties or sigma properties. So first we can separate these the terms of these summations. So we can separate 2k as one summation of this, and then minus 1 as one summation of this. So I'll be right back once I've written this. Alright, so we can rewrite these as follows. Next, I'm just going to use another sigma property. Since the coefficient of k is a constant, which is 2, we can extract that out of the summation. So let me just move the equal sign a little bit further, so it can look like this. We can do the same for 4k in this case, so that will be right there. And this looks probably messier, but this actually brings us some motivation to use a very famous summation. So let me just write that for you guys. So the sum as k goes to 1 to n of k. So we can rewrite this as 1 plus 2 plus all the way up to n. And notice this is just a triangular number and is defined as n times n plus 1 over 2. And we can do this for this summation. However, there's a bit of problem. The bounds of this summation is not equal to this. So we have k is equal to 199 for the lower bound, and we have k is equal to 1. However, we can use another sigma trick or summation property. We can rewrite this as follows. So it'll be like this. So notice that this term has changed, and if you want to deform this back to this part, you end up with the same result, since this k equals to 1 to 198 terms will cancel, and leaving us with a bound of 199 in this case, since the 199 will cancel with one of these. So that's the trick behind that. And therefore, we have all of our sigmas, at least, will be exactly in the form of our special summation, as I would call it. So we can just rewrite this. We can use this formula. So once you've done that, you end up with something like this. Alright, so this is what you should end up with. So notice that we have substituted our special formula or special tool for each of the segments. Now you may be wondering, how do you get this value? Well, notice that when k goes from 1 to 198, you end up with 1 plus 1 plus 1 plus all the way up to plus 1, a certain number of times, which in this case will be 198. Same case for the other one, but in this case from 199 to 300. So the way to evaluate that is to count how many ones are there in this case, which will be 198 and 102 respectively. And once you've calculated this, you end up with a result of 141,142. And that's our answer. Alright, so this is question 2. Let's jump into question 3 and our final question. Alright, for question 3, which is the last question, given a sequence t of 1, t of 2, t of 3, and so on, with the property that t of n plus 1 is equal to n plus 1 times t of n. And this is true for some integer n which is greater than or equal to 1. So you might recognize this. This looks like a recursion definition of a sequence. And I'll let you guys just search about that. And also we're given that t of 1 is equal to 1. So you might want to find an explicit form for t of n. So for part A, we need to generalize a formula for t of a plus 1 all over t of a. And I forgot to mention this in the question, but a must be a positive integer. Hence, evaluate t of 2022 over t of 2021. And for part B, when is t of m is equal to m? Otherwise, t evaluate at some integer is equal to that integer itself. And that integer must be positive. And we must explain why this is, or they are, the only solutions. And for the last part, we need to find all positive integers a satisfying this inequality. So we have 20 is less than t of a, but it's less than 2021. Alright, perhaps I'll just try to find an explicit form for t of n. So let's just kind of like play around with some values. So we know that t of 1 is equal to 1, t of 2 is equal to, based on this definition, we have 2 times t of 1, which is 1, is equal to 2. And we have t of 3 is equal to 3 times t of 2, which is 2, is equal to 6. Next we have t of 4, which again based on the definition, we have 4 times t of 3, which is 6, is equal to 24. And you can just do this all and on, and you might recognize a pattern. 1 is equal to 1 factorial, 2 is equal to 2 factorial, 6 is equal to 3 factorial, and 4 is equal to 4 factorial, and so on. So this way convinces us that this is a factorial sequence. So we can immediately define t of n to be equal to n factorial. And in case for some of you that are unclear, you may prove this by induction. So that is the explicit form for t of n. And we're ready to tackle part A. So we need to write t of a plus 1 over t of a. Substituting the definition or the explicit definition, we will have a plus 1 factorial over a factorial. We can rewrite a plus 1 factorial slightly differently as so. So if a plus 1 times a factorial over a factorial. Notice if you undo this part, you end up with the same part of here. And notice that a factorial and a factorial cancels very nicely. And since we know a factorial is never equal to 0 in the case of a being positive integers, this is equal to a plus 1. So we have generalized a form. Now we can do the same trick to evaluate t of 2022 over t of 2021. So using this formula, where in this case a is equal to 2021, That'll be 2021 plus 1, which will be 2022. Alright, so that's it for part A. And for part B, we need to find a positive integer m such that T of m is equal to m. And we know that T of m is equal to m factorial. So we need to find the case where m factorial is equal to m. And if you look at this case, we know that we have two obvious solutions, T of 1 and T of 2, since they are both equal. And in fact, m is equal to 1 or 2 are in fact the only solutions. And for why is that the case? Well, notice here. So notice that the inputs of the T of n function or T of n sequence are increasing kind of arithmetically. So this is added by 1 and so on, so on, so on. While on the right hand side, these terms actually increase, let's say, predicatively or geometrically, if you were to say that. And of course, multiplying things grows faster than adding things. And we must ensure that that multiplication is probably bigger than or equal to 1. Or at least it's bigger than 1 to make it increasing. And the larger the number that you're multiplying with, the more growing, or the faster the numbers will grow. So if you visualize that in a graph, so this will show a linear graph which increases arithmetically, and this shows a exponential graph, or a graph that is similar to m factorial. So as you can see, the differences in the slopes. So of course, this graph or this function will grow faster than this. However, it will be kind of like explicitly smaller than the one that is growing slowly. So that's just a brief explanation of how this thing works. So with that, we can easily say that the only solutions are m equals 1 or 2. Alright, and finally for part C, we need to find all positive integers a such that T of a is between 20 and 2021, not including 20 and 2021. Well, we can just experiment the values of a, since we know T of a is equal to a factorial. So let's see. We know that from here, T of 4 is a solution. We know that, let's see, let me just clear some space. We know T of 5 is equal to 5 factorial, which will be 120, which is also a solution. And we know T of 6 is equal to 720, which is 6 factorial, which is also a solution. And T of 7 unfortunately does not satisfy this, since it is 5040, which is way out of the bounds of 2021. So the only a values that satisfy this are 4, 5, and 6. And that concludes this question as well as this video. So hopefully you guys enjoyed this. Please subscribe for more videos, and I'll see you guys in the next one. Goodbye.